Okay, so in this video, we'll talk about a new definition about being a series being absolutely convergent. So a series is going to be absolutely convergent if the series that we obtain when we put absolute value around each term is convergent. So the term we're defining here is this one, that the series is absolutely convergent. Sometimes we can say it converges with absolute value or it converges absolutely. But if the point is, if we put absolute values around it, the series converges. So how are these different? Well, my original series could have negative terms, right? That's a big idea. This ANs could have been positive or negatives, and here we're saying we're making all the terms positive, so we're ignoring any negative signs. Sometimes one will converge and the other will not, or sometimes both will converge. So my second definition is just to say that a series is going to be called conditionally convergent. So this is the term we're defining here, conditionally convergent. If it is convergent, but not absolutely convergent, okay? So what this is saying is that this one converges. Let me write this down. This one converges, but this one does not. Okay, so let's stop and think this for a minute. Do we have any example of a series where this happens? So I'm going to give you a moment to do it while I write these things down. But so think of a series that if you put absolute values around it, it will convert. It will, sorry, if it, as it is, it converges. So some terms are negative, but if you put absolute values around it, then it will not converge. So maybe somebody already thought about that. The example we have that we have talked a lot in the past is the series that is alternating. Put a -1 to the n. Oops, that's very ugly. Parentheses. So the harmonic series that's changing signs. Put it like that or like that, it doesn't matter. This one converges. So I'm going to write is conditionally convergent. Right? Because as it is, it converges, but if you put absolute value around it, if you put absolute, I'm going to write all this, and put absolute values around it, well, it becomes just a harmonic series, which is a divergent series. Okay, so this is our first example of a conditionally convergent series. Okay, we have examples where it doesn't happen, right? This one both will converge because this one converges absolutely because it converges as it is, and if you put absolute values around it, it will still be a geometric series, right? So this one is a geometric series, converges. It's a geometric series with r equals to -2/3, but the absolute value of r is less than 1. That's all we need for geometric series to converge. And if you put absolute values around it, all we're going to be doing, if you put absolute values around it, all we're going to be doing is erasing that -2, and it's still going to be a geometric series. But now r is positive 2/3. Right? So it still converges, right? So this one converges absolutely. So this series converges absolutely, or absolutely convergent. Okay. Okay. So the one big thing that we can use this for is that if a series converges absolutely, then the series is convergent. This looks a little bit too much to asking, but sometimes in my example you're going to see it's easier to prove that it's absolutely convergent than proving that it's convergent, because we can just ignore the fact that it's alternating. So let me just show you, for example, what this means. I want to, how do you prove this? So we will prove this like this. First thing to notice is that if I have any number, okay, we'll put an, I don't know if my an's, so I'm gonna get a series. Sorry, I'm gonna pretend a series like this. Let me write this line down like this. Let me start. So we're gonna assume we have a series of terms that converges absolutely. So what this means is that this one converges, right? So I'm going to stop writing these symbols, but okay. So we're going to assume that that's true. So if the one we know it converges is with absolute value signs. We do not know, or we haven't proven that the one without the absolute value signs converges. Okay. So let's grab our ANs. Our ANs, I don't know if they're positive or negative, but the trick here, important key thing is that if I add the absolute value of AN, that becomes, this cannot be negative, right? If AN was negative, you add in this absolute value, which is positive, so make it 0. So this is, if AN is negative, that's 0. And if AN was positive, this is 2 times the absolute value of n, right? So just because if AN is negative, in this side you add in one positive and one negative of the same values, so it's 0. So you can put greater than or equal to 0. And if AN is positive, then AN is the same as its absolute value, and you get this, right? So this is true for all n. It doesn't matter what number AN is. Okay, so now this means that the series, this guy converges. Why? Because, sorry, this looks very ugly right here. This converges because it's just using a comparison test. They're only positive terms, and it's smaller than, each term by term is smaller than this one, that we know converges, right? Because we're assuming the absolute value of it converges, so we know 2 times the absolute value of it converges. So by using a comparison test. Okay. And now, so if we know that, okay, we know that this series converges, okay? So if we know that, then the key point here is to say, well, if you have the series AN, there's a trick to write it like this. AN plus the absolute value of AN and take away the absolute value of AN, right? I seem like I did nothing, right? So if you add the absolute and subtract the absolute value of AN, you stay with AN. The point is that you can break this up as the sum of 2 series, because each of the, you cannot always do this, okay? You can do this because this first series, right here or up here, is like 1, all it's inside the sum, and now I'm putting it inside 2 terms, right? And why is that true? Because this one is convergent, because I have it over here, right? It's this one. And this one converges because it's my hypothesis from up here. So if you can break up a series like the sum or the differences of 2 series, then it is true, each one of those. It converges, so the sum will converge. So that's convergent, this one converges, so this one converges. Okay, so this is the proof that if you have a series that is absolutely convergent, then the series itself converges. Okay, how do we use this? Well, we use this like this. In an example like this one, this is alternating. See, the problem when we're thinking about examples like the one I did over here, we're thinking, well, they're alternating. I have the alternating series test, which allows me to prove things already, or stuff like that, like this one up here. Yeah, the problem is, in series like this one, I know that some of these terms are positive, but I have no way to control which ones. So this is not an alternating series. I do not have a a way to write the cosine n over n like a nice formula to say they're alternating like negative 1 to the power of n. That's not, I do not know that, right? But I can prove easily that the series if I put absolute values around it, these are just positive terms, correct? And because they're all positive, the cosine is an absolute value less than 1, so it's less than erasing the cosine part, right? So putting the absolute values on this side allows me to say, well, since they're all positive, now I can bound it by 1 over n squared. And this is a this is a P series, because it's a P series with P greater than 1. So since I proved that this series up here is absolutely convergent, because if I put absolute values around it, it converges, I know that then it is convergent. That's what we just proved. Right? The theorem we just proved says exactly that. That if you prove that the series is absolutely convergent, then it is convergent. So, and the way to prove this one is, well, you have the absolute values around it. If you put the absolute values around it, then you can bound it by only this one, and then you know it converges. Okay. Okay. So I think I have one more. This is an alternating series. We could prove that it converges if you wanted to. It has this alternating pattern, but I'm going to do it in an easier way. This, by the way, is a problem that is in one of my exams, and I'm not going to do the steps carefully, but I'm going to do the same argument. If you put these terms in absolute values, I forgot this part. If you put the absolute values around it, it becomes this one. And now, since you only have positive terms, you can apply this one to the integral test. Okay. I know that since this is alternating, you can also use the alternating series test. You have to prove that the function of 1 over x, ln x is always decreasing, which is pretty straightforward. But I just want to give you the idea that this, you can also do it now, but putting the absolute values around it, and now using integral test on this one. And this was something that we used, usually comes as an example with the integral test. Okay, so this is absolutely convergent, and the next video will be about the ratio test.